And talk a little bit about the free body diagram for an object that is rolling on an incline. So we've got a ball and we have three forces that are acting on it. The ball has some mass, so it has a weight. And so there's a force of gravity that acts straight down. And we can imagine that force of gravity in its components that are parallel to the inclined plane and perpendicular to the inclined plane. The normal force acting on the ball acts at the, so it's contact force, acts at the point of contact between the incline and the ball. So the normal force is going to be big enough to cancel out this component of the weight. So mg cosine theta. And then what prevents the ball from just sliding down the incline is that there's a force of static friction at the point of contact. So the other component of the contact force, the parallel component of the contact force between the ball and the inclined plane, is static friction. And it's static friction, not kinetic friction, because the ball is going to roll. So this point of contact is instantaneously at rest. And there's a few insights out of this free body diagram applied to this idea of rolling. We have equilibrium vertically. It is the component of the weight that's parallel to the inclined plane and the force of static friction that determines what the linear acceleration is of the ball. So if we just look at the center of mass of the ball and its acceleration, mg sine theta is trying to speed that up. Force of static friction is trying to slow it down. And then the torque to rotate about the center of mass has to come from the force of static friction. Normal force can't cause that torque because its line of action passes through the center of mass. The weight of the ball can't provide that torque either because its line of action goes through the center of mass. So it is the force of static friction that exerts the torque about the center of mass of the ball to make the ball roll. And you could also do an analysis where we imagine that the rotation axis is this point of contact between the ball and the incline that's instantaneously at rest. And in that case, normal force doesn't cause a torque. Static friction doesn't cause a torque, but it's this part of the weight that makes the ball roll around that instantaneous axis of rotation. So you wind up with the same physics, but for a different axis of rotation. All right, let's try a couple questions. See how we're doing. So I have a solid disc and a hollow ring. We're going to roll down an incline. The ring will be slower than the disc if, which of those is true? Their masses are the same, their radii are the same, both mass and radii are the same, or the ring is always slower, regardless of the relative values of mass and radius. So which one of those do you think is correct? Talk it over with your physics neighbor, and then let's compare answers. All right, the ring is always going to be slower. It doesn't have any other possibility. So it should make sense that the mass cancels out. If you think of it in terms of energy, the gravitational potential energy is proportional to the mass, but kinetic energies, both rotation and translation, are proportional to the mass. So the mass cancels out. What's a little bit more subtle is that the radius also cancels out. The radius cancels out in this because you have the rolling without slipping, or the smooth rolling condition. So the ring is going to move forward one full circumference of the ring every time it goes through a 2 pi radian rotation. So the speed um, in terms of the angular speed, it's going to be the linear speed divided by radius. That radius precisely cancels out the powers of the radius and the rotational inertia. So both mass and radius cancel out. All that matters is how the mass of the object is distributed relative to the rotation axis. The more of your mass you have concentrated on the rotation axis, uh, the less it contributes to rotational inertia, and you're going to have a higher proportion of your kinetic energy in translation as opposed to rotation. So for any mass and any radius, a ring is always slower than a disk, and a disk is always slower than a solid ball, for example. All right. Now I have a hollow cylinder of mass m and radius r, rolls down an inclined plane, and I have a block of mass m, same mass, slides down an identical inclined plane. Complete the following statement. If both objects are released at the same time, which of those five is true? So you think about what you think the answer is, talk it over with your physics compatriot, and then resume the video and we'll compare answers. All right. What is true is that the block is going to have to reach the bottom first. So let's go through and make sure the reasoning is clear on these. So the block will reach the bottom of the kinetic energy. That's false. They both have the same kinetic energy when they reach the bottom because they both have the same mass. They fall down identical inclined planes. It's just that the cylinder has some of its kinetic energy in rotation and some in translation, whereas the block has it all in translation. So a cylinder can't reach the bottom with greater kinetic energy either. They both have the same kinetic energy. They do not reach the bottom at the same time, and the block will reach the bottom first because all of its initial gravitational potential and energy is becoming kinetic energy of translation. Uh, for the rolling cylinder, some of its gravitational potential energy is becoming kinetic energy of rotation. And that does not contribute to translational motion. So you are using up some of your potential energy to spin up the cylinder. And that spinning up does not make the cylinder go forward. So comparing a hollow cylinder that rolls to identical mass block that slides, the block is always going to get to the bottom first.